Hello and welcome. In this video, we are going to talk a bit more about the heap data structure. In the last video, I let you know that the heap is a complete binary tree. But there is another important property that a heap needs to satisfy, and that is known as the heap invariant. And the heap invariant also determines the type of heap that we are dealing with. So heaps can be of two types. One of them is called a max heap and the other is called a min heap. And the type of the heap is determined by the heap invariant. So the heap invariant for a max heap states that if you pick up any node within the structure, the value contained by that node will be greater than or equal to the value of all of its successors. Similarly, the heap invariant for a min heap states that if you pick up any node within this heap, the value of that node will be less than or equal to the value of all of its successors. So here are a few implications of the heap invariant. If we are dealing with a valid heap, that is, it is a complete binary tree and it supports and it conforms to the heap invariant, then if the heap is a min heap, then the value contained at the root is actually the minimum of all of the values present in the heap. Why? Because the value contained at the root needs to be less than or equal to the value contained by all of its successors. And therefore we can safely assume that this is the least element in all of these nodes. Similarly, for the max heap, we can assume that the root element is actually the maximum of all of the nodes that are present inside the heap. So this would give you kind of an intuition to how the get max and get min operations support a constant time query complexity, basically. Now we shall move into how we can actually create the heap from a given array. How can we create the heap? Now in the previous lecture I told you that a heap is internally represented with an array and two functions, which are the left child and the right child functions. And these three things together can represent this structure. So let us say that we have a heap, okay? And the values contained by it are something like this: 0, 1, 2, 3, 4, 5, 6, 7, 8. Alright? So in this case, if I tell you that this is a min heap, then you can verify that it is a valid structure, because if you pick up any node and see its value, it is either less than or equal to the value of all of its successors. If you see 2, it's less than 5 and 6. If you see 0, it is actually less than all of these guys over here. So this is a valid min heap. But my question to you is, what if the value contained here was not 0 but 100? How would you fix this anomaly within this min heap? And this is actually a very important question, because it is going to introduce us to a very important function, which is the sift down function. And this function is very crucial for the creation of a heap, and as well as deleting an element from the heap. So let us see what we would do to fix this anomaly over here. So in order to fix this, here we already know that this guy and this guy, both of them are heaps, alright? So if you take this subtree, if you take any node within it, you're going to see that all of the nodes satisfy the heap invariant over here. So only this node over here is completely messing up the structure. So how do we fix that problem? The key thing to do is we are going to check the value of this node, the value of its left child, and the value of its right child. Alright? And we are going to select an element out of its left child or its right child and replace the value of this node with that child. Now notice, we cannot replace 100 with 2, because if we did that, then 2 would be above 1, and that would violate the min heap property again. So what we can do is we can propagate the value 100 downwards and move the value 1 upwards. Okay, now you can see that this portion in itself is indeed a heap. Alright, but we are not done. We can still see that this region is not a heap because this value is more than all of these guys, and that is not the min heap invariant at all. So what do? We again do the same thing. We remove 100 and select one of its children and propagate its value upwards while putting 100 in place of the child. Alright, now again we see that the min heap property is violated, so we propagate 100 again downwards, select one of its children, place it at the top, place 100 down, and now we can see that the min heap property is actually satisfied by all of the nodes in the tree. So this was a general introduction into what the sift down function is. In the next video, I shall tell you how we can write down the code for this entire operation, and we shall see more about creating the heap and also about getting the maximum and the minimum out of a heap with ease.